Good morning and welcome to section 2.3. We're going to be looking at real zeros of polynomial functions, and this is the unit where we're going to practice using long division and synthetic division. And we're going to take some big polynomials and divide them by other polynomials, and we're going to use those to find rational and real zeros of the polynomial functions. So we're not getting into imaginary numbers yet. That is in the next unit. These are just real zeros and rational. And so if you recall, a rational number is any number that can be written as a ratio. So those are fractions and decimals. And notice also we don't have irrational numbers in the list. So if you remember, whenever you use the quadratic formula, you could get some square roots and things, and I'm thinking we're not quite there yet either. So I apologize for the quality of the copies here. Something went wrong with the printing, but I'm not really going to use what's in this box too much because rather than writing down a definition of some of these things, I'd rather just show you how to do it. So let's go ahead and skip on down to this section here where we have a few facts about long division, and then I'm going to show you an example. So when dividing a polynomial by another polynomial, if the remainder r of x equals 0, then d of x divides evenly. So if there's no remainder, that means it divides evenly, and that means it is a 0. So we do have a couple of terms here which are actually new to me. Not that improper and proper fractions are, but with respect to polynomials, these are going to be important a little bit later when we're graphing rational expressions, so I want to go ahead and highlight these. If we're going to divide some function f of x divided by d of x, and actually, yeah, we're not just talking about remainders, we're just saying any rational expression. It's improper if the degree of f of x is greater than or equal to the degree of d of x. And remember, the degree is just the highest power of the highest variable in the polynomial. And so we would say it's a proper expression if the degree of f of x is less than the degree of d of x. So the improper, that would be like if you had x squared over x. It's just the degree is higher on the top. And then it's proper if you have like x cubed, say 3x cubed over 3x cubed minus 2 over x squared plus 1. Say, you can just look at the degrees, and if it's higher on the top, then that is going to be improper, and then proper is when the degree is higher on the bottom. So I could just switch these around and have the lower one on the top. So that's my example of a proper one. So before applying the division algorithm, so we're getting ready to divide these polynomials, there's a couple of things that you need to do every single time. First, and I love a list, so rather than writing in a paragraph, I'm going to write you a list. Write the dividend and the divisor in descending powers of the variable. So the dividend, that's the thing that's being divided. The divisor is the thing that goes into it. And we're going to say in descending order of the variable. That's standard form, so this should be familiar to you. And then after you do that, if there are any gaps, we're going to, and by gaps I mean, if we look at example 1, we have 3x cubed plus 4x. So there's a gap right there where the x squared term would be. So we're going to call that insert placeholders with 0 coefficients for missing powers of the variable. Placeholders with 0 coefficients for missing powers of the variable. And I was going to use that space to work out this problem. So you can squeeze it in down here, but I am going to go ahead and work this problem on a separate sheet of notebook paper. So our problem is we want to divide 3x cubed plus 4x minus 2 by x squared plus 2x plus 1. So I'm doing a quick check, and I see that they're both in descending order of the variable. So I just want to put in a 0x squared right here when I write down the problem. So this is the dividend and this is the divisor. So when I set this up, we go to my notebook paper and I'm going to make my division bar. So 3x squared plus 3x cubed plus 0x squared plus 4x minus 2 divided by x squared plus 2x plus 1. So this 3 here. So the way I'm going to do this is I'm going to look at my initial terms and I'm going to say, what would I need to multiply x squared by to get 3x cubed? Or what is 3x cubed divided by x squared? Well, it's 3x. And then I'm going to do a distributive property, and I'm going to multiply 3x by each of the terms here, and I'm going to line them up underneath my other polynomial. So 3x times x squared is 3x cubed. So whenever you subtract, this one should always drop out. Now 3x times 2x is 6x squared. 3x times 1 is 3x. Now, just like when you're dividing, you subtract. So I'm subtracting each term. So if it's positive, I make it negative. If it's negative, I make it positive. So this is 0. 0 minus 6 is negative 6x squared. 4 minus 3 is positive 1. So now, again, I'm looking at my initial terms. Negative 6x squared divided by x squared. If I do a negative 6 here, when I multiply it out, I'll get negative 6x squared, and these will subtract. And then, I want, just like long division, I'm going to bring down my next term. So negative 6 times 2x is negative 12x. Negative 6 times 1 is negative 6. Now, since I'm doing subtraction, I can think of it this way. Or I can go ahead and do minus minus 6, so that's plus. Everything becomes the opposite. So negative 6 plus 6 is 0, so I don't have to write anything. 1 plus 12 is 13x. Negative 2 plus 6 is plus 4. And since I can't divide x squared 13x by x squared, this is my remainder, so I go ahead and write it like this: 13x plus 4 out of x squared plus 2x plus 1. So that is example 1. So this means it doesn't go in evenly, which is no big deal. It just means this is not a 0 of that function. And we'll do some more examples of that in class, because now we are going to move on and look at some synthetic division. So you know what, before I look at synthetic division, I just want to write a few things down for you guys in it's called the division algorithm. So what we just did with that long division, we followed a certain process. So I just want to define a few of the terms. So here we have the dividend. Here we have the divisor. Here we have the quotient. And here we have the remainder. Okay, and so if I were going to write it using that division bar, so the quotient is the answer. The remainder is up here. The divisor is out here. And the dividend is what goes underneath. Okay, so in our last example, we had our original function. So that would be the f of x. It equals the dividend, x squared plus 2x plus 1 times the quotient plus that remainder. So I want to make sure that I'm not using words that are confusing. Okay, so synthetic division. This is a nice shortcut that you can use. The only issue is we can't use it to divide any higher order polynomials. Okay, so if we have an x squared term, then no, we can't use synthetic division. If we want to do x plus 4, we can divide any polynomial by a first order binomial. So that's it. I'll say degree is greater than 1, and here I could say the degree equals 1. So we are going to do synthetic division, which you've done this before. So we're going to create an array using the coefficients of all of the terms in the divisor. Now we still have to follow that same process where we fill in any gaps. So if I want to divide 2x to the 4th plus 5x squared minus 3, I have to fill in a 0x cubed and a 0x here. So if I'm making my array, the coefficients are, and I probably wrote this wrong, 2, 0, 5, I did. I don't have any whiteouts, so we're just going to deal with it. 2, 0, 5, 0, negative 3. So I should have written that small up here, and then I would leave myself some room to subtract. So I just need to like extend my bar here a little bit. Okay, and so I'm dividing it by x minus 5. So I am going to put on the outside of here, what would be the 0 if x minus 5 were my factor? And so that's actually a positive 5. So here is the process. You start by bringing down the first term, 2. Then we go 2 times 5 is 10, and then we subtract. So, no, then we add. Sorry. 0 and 10 is 10. 10 times 5 is 50. 5 plus 50 is 55. 5 times 55 is a big number, 275. Add them up. And 5 times 275 1,000. 1,375. So if we add -3, then we get 1,372. So that is the remainder, which tells me these do not divide evenly. Okay, so even though we have a remainder, we can still say our solution to the original division problem is we drop 1 down from the degree which we started. So this coefficient is now the coefficient of an x cubed, and then plus 10x squared plus 55x plus 275, and then this remainder plus 1,372 over the original divisor. So we will do some more examples in class and hopefully get somewhere. You know what? I'd like to go ahead and do one that divides evenly, or where the numbers are at least just a little bit nicer. So let me do one more example. I'm going to go to my notebook paper, and I'm going to go with example 2. And I'm going to ask you guys to divide x to the 4th minus 10x squared minus 2x plus 4. Divide that by x plus 3. And so we're going to follow the same process, and we have to do those same steps at the beginning. So we need to fill in, we don't have an x cubed term, so I need to fill that in with a 0 term. Let's see, x squared minus 2x plus 4. Okay, so now I've got a good polynomial, and so I'm going to create my array. And so on notebook paper, I would just draw it where it takes up 2 lines, and then I'm going to go with my coefficients. So I have 1, 0, -10, -2, and 4. And then the 0 is what goes on the outside, so that's a -3. So to follow the process again, I'm going to bring down a 1. 1 times -3 is -3. 0 plus -3 is -3. -3 times -3 is 9. Add them up. -3 times -1 is +3, and we get a 1. -3 times 1 is -3. So we didn't get a 0 remainder, but at least the numbers in this one, I feel like they're friendlier, so I think it's a better example. So the solution to this division problem is, so I take this 1, and that's going to be the coefficient of an x cubed term now, minus 3x squared, and you just go in descending order of the variable, minus x plus 1, and then 1 was my remainder, so I go plus 1 over the original divisor, which was x plus 3. Okay, so I think that's a much nicer synthetic division problem. So now let's talk about the remainder. To use the remainder theorem to evaluate a polynomial function f of x at x equals k, then the remainder is r equals f of k. Okay, so what does that mean? We're going to take our function. We want to evaluate it at x equals 5, so I'm just going to go ahead and do a synthetic division, and I'm going to write down my terms, and I'm going to fill in zeros for my x cubed. I've got a 0 for an x term. So if I start at x to the 4th, I better have 5 numbers going across here. So I'm going to do my synthetic division to bring down a 2. 2 times 5 is 10, 0 and 10. Oh, this is the same problem that I had to begin with. Sorry. So I kind of already know what everything's going to turn out to be. So my remainder was 1,372. So if I were to substitute 5 into this function, I should get 1,372. And I just need to prove that to myself. So 2 times 5 to the 4th plus 5 times 5 squared minus 3. So 5 to the 4th, 625, not plus, times 2, plus 5 times 25, that's 125, minus 3. Oh, look at that. Okay, so I think, I don't know which is easier, to synthetically divide it or to just plug it in, but we are just going to say, yay, we know that the remainder theorem exists, and move on. So our goal, though, we're going to be using synthetic division to find zeros of functions. So our goal is to get a factor and synthetically divide it, and then if x minus k is a factor, so I'll say if and only if f of k equals 0, and that means you get no remainder when you divide it out. So we still have 2 more pages of notes, and this video is already on 21 minutes, so I'm going to stop it here and call the next section part 2.